Hello everyone, I am Harshit Joshi from Microsoft, and today I'll be presenting our work, Neurosymbolic Repair for low-code formula languages. So most programmers write code which often contains bugs. Now there is a spectrum of errors which ranges from simple bugs such as syntax errors to complex and hard to fix concurrency bugs. Our work focuses on the left side of this spectrum, which includes syntax errors and some simple semantic bugs. Now, the errors which require very few edits, we call them last mile errors. And these errors, so the special thing about these errors is that they do not require additional context. And we just by looking at the formula or the program, we can figure out what needs to be changed. And these kinds of errors are usually hard for low-code users to fix and identify. Low-code users are the users on Excel and PowerApps. So here are some examples of last mile errors in two very popular low-code domains, PowerApps and Excel. In the first row, we see that there are faulty formulas which require very few edits to fix them. However, if we look at the compiler messages, they are actually quite unhelpful. So let's go over one of the examples. So in the first one, you'll see that the user has missed a closing parenthesis after the text token. However, the compiler complains that it expected a closing parenthesis at the end of the formula. So now that we have seen what are last mile errors, and now the thing is that we want to fix them automatically. Moreover, there are some similarities in the kinds of errors that people make in low-code domains. Therefore, we want to avoid repeating the work for multiple languages, and hence we create a repair framework, LaMirage, which can generate repair engines. So once we have the domain information, we can provide that to LaMirage and it can generate a repair engine for that given language. So for example, if you have Excel, we require some domain information regarding Excel. We provide that to our repair framework, LaMirage, and it can generate a repair engine for that domain. Now let's take a high-level look at LaMirage, the last mile repair engine generator. To create a repair engine for a domain or a language, LaMirage requires domain-specific information, which will be provided by the repair engine developer. So the repair engine developer needs to provide us two things. One is context-free grammar and domain-specific strategies. Let's look at each of them, what these are. So the context-free grammar that the repair engine developer provides us needs to be annotated for unreliable tokens. Now, these unreliable tokens are the tokens that we are allowed to edit while we are producing the repair. We went over a lot of user forums for Excel and PowerApps, and we found that these are the tokens where users usually make a lot of mistakes. And they are like delimiters, parentheses, commas, dots. The one great thing about this is that the repair engine developer has the flexibility of annotating or bringing in domain knowledge, and they can annotate how many numbers of unreliable tokens they want to annotate. So now once we have the context-free grammar, the thing is that with context-free grammar can only facilitate syntactic repairs, but the last mile errors, they go beyond syntax repairs. So since they go beyond syntax repairs, we need a way of fixing semantic repairs. For this, we have domain-specific strategies which can perform these semantic repairs. Now, these domain-specific strategies are basically pluggable heuristics which we can write in a couple of lines of codes. And we have a set of these domain-specific strategies which can apply to multiple low-code domains. The examples of these domain-specific strategies, the types of repairs that they help us with are like, for example, wrong functionality, misspelling, and some other tokenization issues. Now, to summarize, the repair engine developer provides us with context-free grammar, which drives the generic edit operations, which help in syntax repairs. whereas the domain-specific strategies enforce the semantic repairs. Now that we have the two components provided us by the repair engine developer, let's see how we can use them to enumerate repair candidates. So what we do is we construct a LL parser from the annotated context-free grammar, and we perform syntax-guided candidate enumeration. So for a given buggy formula, we process the input token stream as done by most of the LL parsers. But if we hit an error state, we enter the repair mode. Now, in this repair mode, we enumerate candidates using the context-free grammar and domain-specific strategies. One important thing to note is that the error state can be raised by various methods. Either it could happen by when we are parsing, if there is some token which violates the context-free grammar, then we can enter the error state, or it can also be raised through heuristics, or they can be predicted by external modules. Now, one important thing to note is that the errors are not always where the compiler detects them, and they can occur some tokens earlier. So, for example, in this case, the compiler error was detected at this colon, but maybe we want to perform a repair at the opening parenthesis. So the repair engine that LaMirage creates has bounded backtracking depth. And so what it does is it basically stores the parser state while parsing the formula. And then we can backtrack to specific states to generate repairs. For more information, there's more information in the paper on how we do this backtracking, and I'll be happy to talk about it later in the Q&A session. So although our symbolic enumeration component has backtracking ability, but this is bounded backtracking ability. So there can be cases where the errors are far away, and the backtracking depth cannot cover it. So one solution is to have a very large backtracking depth, which covers most of the formula. However, as the backtracking depth increases, the time taken to enumerate repairs can also increase. Therefore, in such cases where the error is further away from where it was detected, we use a neural error localizer. The neural error localizer learns to predict error locations in a formula and provides potential error location for the symbolic enumeration. Now let's take a look at an example. So in this Excel formula, the compiler raises an error at the end of the formula, and it complains about the missing closing parenthesis. However, the actual error is that the user missed a closing parenthesis after the cell reference C1. And the thing is that the backtracking depth does not cover the error location. Therefore, we use a lightweight pointer network, which is trained on synthetically generated buggy and fixed pairs. Now, this pointer network, given a formula, it tries to predict potential error locations, and then we give these specific error locations to our symbolic enumeration system. Now, finally, once we have generated all the repair candidates, we need to rank them so that we can surface the most probable repair to the user. Now, our repair for ranking the repairs, we use a two-step process where first we rank the candidates based on the edit distance between the original buggy formula and the repair candidate. We follow the intuition that in last mile errors, fewer the number of edits we need to make, the better the candidate is. However, sometimes there can be multiple repair candidates which have the same edit distance. To resolve this, so to give the most probable candidate, we train a neural ranker, which uses CodeBERT, and it is trained on the well-formed formulas, and it tries to predict the most likely unreliable token sequence. So finally, once we have all the ranked candidate list, we can now provide top 1, top 3, or top 5 repairs to the user. So coming to the evaluation part, we extensively evaluate our work in two very popular low-code domains, which are Excel and PowerApps. we manually annotate ground truth repairs for 200 formulas in each of these domains. Now, these formulas come from real user forums, and some of them come from the anonymized production telemetry. For evaluation, we match the produced candidate with the ground truth. So we also compare our system to the state-of-the-art symbolic and neural methods. So first of all, we evaluate how the existing error recovery tool works in Excel, and by what degree can we improve this existing system. Then we compare to GRM tools, which is the state-of-the-art symbolic parser recovery system. Now, the next system that we evaluate is BiFi. It is a transformer model which has two neural components. One is a neural breaker and the other one is the neural fixer. And both of them are trained simultaneously, where each of them, the one module first tries to break the good formula, and now the broken formula needs to be repaired by the neural fixer. We also try out two APIs from OpenAI, which are Codex and Codex Edit. So in Codex, we provide a prompt, and Codex needs to complete the prompt and generates the repair. On the other hand, in Codex Edit, we provide the original formula, and now Codex Edit performs the changes to the original program. So the difference is that it doesn't complete, it indeed makes changes to the original prompt. Now, here the results table. I'll go over the three key insights that we derived from these results. So we see that the neural models are better than the symbolic error recovery parsers. Although this is a conscious design decision from GRM tools, as they want to compile the formulas of the programs faster, and they don't have the backtracking capabilities. Since they don't have the backtracking capabilities, it also limits the expressiveness of such tools for repair. Now, LaMirage, which is a neurosymbolic method, outperforms the neural methods. And the reason for this is that the neural methods cannot guarantee syntactically correct programs. Moreover, another key difference is that we have domain-specific heuristics or strategies in LaMirage, which can improve the performance by just adding a couple of lines of codes, whereas we will need to retrain the neural model to do the same, to learn new kinds of errors and to do the similar kinds of repairs. Now, another interesting observation is that the performance of neural models decreases as we move on to the PowerFX domain. And this is likely because PowerFX is a low resource language. You don't have a lot of data for this in wide, and therefore these neural models haven't seen a lot of PowerFX data. Now, finally, through our work, we show that symbolic and neural methods as separate systems are not enough. And however, we can combine the strength of symbolic and neural systems. The symbolic system helps us in fast enumeration and generating valid repair candidates. On the other hand, the neural model, although they cannot guarantee us correctness of candidate, they can help us in other things like ranking the candidates and predicting the error locations. So the key insight that we derive from our work is that we can produce correct code which obeys the grammar and satisfies the constraints. On the other hand, we can use neural models where we do not require guarantee over predictions, such as finding potential error locations and ranking candidates. I will end this talk with the catchphrase that why ask the models to balance the parenthesis when we know how to do it. So finally, coming to what are our future works. So we have been exploring how to perform program repair across multiple languages using large language models, which are trained on code such as Codex. Our recent work, Repair is Nearly Generation, shows that how we can generate syntactically correct programs for repair across different languages. This work will be presented at AAA 2023. And also, a final note is that I'm applying for grad schools for fall 2023, and I would like to continue working on neurosymbolic methods for code. So if your lab works on similar research topics, please reach out. Thank you.
I have got a couple of questions. in a way, did you make? I think there has been work on how to repair syntactic errors since many years. And I wonder whether, in a way, you have made your life a bit easier by choosing DSL, by choosing a language that doesn't have that many features. I'm assuming that you did not go into the full macro language of Excel, so that they're essentially only function calls and formulae. Did that make the problem easier?
So that's a good question. I would say we weren't trying to look at what makes the problem easier, but rather what impacts most of the users. So we naturally started out by looking at the user forums and what kinds of errors are there. And yeah, in this work, although we haven't looked into using different macros which are present in Excel, but we are only looking at the formulas which you can type in the formula bar and use those. So this is a different set of errors, which specifically require few edits. So that is the key here. We even in some of our evaluations, we restrict the edit distance to 5 tokens. So wherever we want to generate repairs, and we also want the edit distance to be less than 5. So just focusing on those kinds of errors.
Sorry, I did not place my question correctly. I didn't mean you tried to solve a simpler problem. I was saying, given the earlier work, were you more successful because your language was simpler, had less fewer different structures, and therefore it became simpler? It was a reflection on the outcome rather than a discussion of. I think any work to improve the use of Excel is super useful. It is a widely used language, and it is not studied enough. It's wonderful to have such tools. So it was more about why did you need to develop new techniques? Why would all techniques not work? And perhaps because the language was more restricted.
So one thing is there hasn't been a lot of work done in these low-code domains such as Excel and in PowerApps. The other thing is that, as we have seen through even the state-of-the-art symbolic methods like GRM tools, so these low-code domains have like special requirements, and all of them have so that's why we need to introduce domain-specific strategies, which apart from the traditional coding convention. For example, here users usually use the built-in functions. They don't necessarily create a lot of variables. So there are these kinds of differences which I believe do not directly translate over from traditional coding languages to the low code domains.
Mm-hmm. I was wondering, how does your if you have got any idea, how does your tool compare with I forget now what this Microsoft tool is, but it runs on VS Code and it predicts what you are going to type.
Yeah, it's Copilot.
So, yes, Copilot, exactly, yes. So I know that Copilot does something different. Sorry, carry on.
Yeah, I was just mentioning that Copilot uses Codex as the neural method at the backend. And here we also try to compare with Codex, and we see that we believe that it leverage for language like Excel, which is more common, like at least more common than PowerFX, it performs reasonably well. But as we move to these low resource languages, which do not have a lot of data in the wild, their performance suffers a lot. And yeah, so that is one thing. And it actually, our next work, which we are presenting at AAAI, uses this codecs, which powers Copilot, in a flipped model where the user writes the code, and now this model tries to repair whatever the user has written.
Right. The comparison that I had
it goes
in mind
beyond.
is...
Yeah, okay, go on.
Carry on.
No, I was just saying that it goes beyond low-code domains. In our next work, we also evaluate Python, C, and JavaScript in that work.
The comparison that I had in mind is that I would start typing my program. Let's say the example with the email where I had forgotten to close the bracket. So I start typing the program. Would the Copilot have completed it for me rather than I get to type it wrongly and then it gets repaired? Whether you have done any such comparison of if I were to start typing the erroneous program, whether the Copilot would have completed it for me.
So if you write a erroneous program, it will try to complete the program for you, but the program will still remain buggy. So that is what is currently used in Copilot. But we can try to repair this. So like right now we with things like Copilot, we are just trying to generate next tokens, but it would be good to explore that how we can also edit whatever the user has already written.
And why did you choose an LL parser? Is it easier for the generation of the next token and for the autocomplete, or two questions? Why LL rather than LR, since LR is more powerful? And secondly, why did you talk in terms of the parser rather than syntax trees? In a way, I don't care what you use in order to create a syntax tree.
Yeah, both of them are really good questions. So I think we just use LL parser just for the ease of it, so that we can easily we can take the input stream and I don't believe that we had any specific reason for not using LR parser. We can potentially use LR parsers instead of LL parsers in our work. For the what was the second question?
Why did you talk about the parser rather than a partial syntax tree?
So what in our work, what we are actually trying to do is this is a good question. I can potentially come back to you about this, but there was no specific reason on why we used the parser instead of the syntax tree. I believe it is just so that we can enumerate repairs, and actually some of our next work would be into exploring how we can use syntax tree instead of using the parsers.
Okay. Thank you.
Thank you.
So you mentioned also that you are now applying the work to Python and many other languages.
Yeah.
So all the discussions, all my misgivings about you had the simple languages perhaps invalidated by the fact that you have been able to apply to those languages.
Yeah. We don't apply the same technique. It is a different technique which uses neural model, but yeah, that is where we are going into.
Right. Okay.